Howdy. In this video, we're going to go through a quick example on the simplification and further simplification of a force and couple system. Let's take a look at what we have over here. We have a cantilever beam to which there's some cables being attached and they're applying some loads. And our job is going to be to find the equivalent resultant force and couple moment acting at A, and then the equivalent single force and location measured from A. If you remember, for this type of problems, we have two basic equations. First, that the resultant force is just going to be the sum of all the forces. And to calculate the resultant couple moments, we have to worry about the summation of two terms. The first one is the sum of the moments of any force that does not pass through the point of interest. And then we're going to add it to any couples that are present in this example, in the problem. Now, do you see any couples being applied in this example? The answer is no, right? We have no equal forces that are parallel but opposite directions, so we have none of that. And also, we don't have any arrows that are curved like this. This is usually what the book uses to identify couples sometimes. So, because we have neither, again, the second term on this equation is going to go to 0. So let's go ahead and begin with the free body diagram for this example. I'm going to start by drawing the outline of the body. So I have to go all the way over here, like so. Here's our point A, that's a point of interest. I'm going to go ahead and put the axis already. So this is going to be our X and our Y axis. So once we have the outline, we're going to go ahead and put the applied forces. So let's start with the first one. This is 200-pound force is in the Y direction. So roughly right here, 200 pounds. And then this is me. I just usually like to sweep from left to right. So if I'm going this way, I see the next force, which is somewhere right here. And I have 100 pounds, right? But it's at an angle. We have this slope triangle. So we're going to go ahead and calculate the X and Y components, because to be able to calculate that resultant force, we're going to have to sum the forces in the X, then the forces in the Y. So to figure out, for example, in this one, the Y component is going to be pointing down. This Y component is going to be 100 times 4 divided by 5, which will give us 80 pounds. And then the horizontal component is going to be 100 times 3 divided by 5, which is going to be 60 pounds. Next, we have the 50-pound force right at the end. Oops, and I should have made this one just a little bit longer. Right, so we're going to go ahead and calculate the X component and the Y component of this one. The X component of the 50-pound force is going to be equal to 50 times the sine, because the sine is going to give us this guy, which is the same as the X component. So 50 times the sine of 30 degrees is going to give us 25. So 25 pounds. And then the Y component, which points up, is going to be 50 times the cosine of 30, because that's our leg that is adjacent. And that gives 43.3 pounds. Now, the only thing that's missing from our free body diagram, we have the outline, we have the applied loads, we need the geometry, right? So we know that from point A to the first force over here is 3 feet. From that one to the next one is another 3 feet. And then from this one to the last one is another 3 feet over here. So next we're going to go ahead and start, calculating the resultant force. Remember, we're going to do it in two parts. First, the sum of the forces in the X direction. Remember, our X-axis points that way, so any force that points over here to your right is going to be a positive force. So again, as I sweep the free body diagram from left to right, the first horizontal force, or force in the X-axis that I have, is this one that is 60 pounds. And then I have this other one over here, which is 25. So 60 plus 25 is 85 pounds in the x-axis. Now let's go ahead and do the sum of the forces in the y direction. Again, anything that points up is positive. I'm going to sweep again from left to right. First one that I encounter is this one, is 200. Because it points up is going to be positive, this guy over here, the next one, which is pointing down, is going to be negative. So minus 80 plus 43.3. This is going to be equal to 200 minus 80 is 120 plus 40 is 163.3. The unit is going to be pounds. Right, so now we have the x and the y component. We want the resultant, so the magnitude of that resultant force is just going to be the square root of our two components squared, of the sum of the two components squared. So 85 squared plus 163.3 squared is going to be equal to 85 squared plus 163.3 squared. This gives roughly 184 pounds. So that is the magnitude. Next is going to be the angle, right? And to be able to do that, always we make a little plot, right? So let's plot, or go ahead and plot here the x and the y-axis. Right? In the x, we have a positive 85, so that means this guy points that direction. In the y direction, we have a positive number, so it means this force points up. So we have roughly 85 here, and then pointing up 163. So the force is going to do something like this. So let's go ahead and calculate the angle, which is usually given with respect to the x-axis. So this angle theta. Theta is going to be equal to the inverse tangent of opposite side. So what do we have opposite? Right? Opposite is going to be the y value, which is 163.3, divided by the adjacent side, which is going to be the x side. So 85. So let's go ahead and calculate it. Inverse tangent of 163.3 divided by 85. We have a theta value of 62.5 degrees. Okay, so far what we have already is the resultant. So I'm going to go ahead and make here another figure. This is our cantilever beam. This is our point A over here. Remember, this is y-axis. This over here is the x-axis. And our resultant force has a magnitude of 184 at an angle of 62.5. So roughly something like this. 184 pounds. And that angle is 62.5 degrees. So we have the first part of the problem done. The next part is to calculate this couple moment. Again, we're going to use this formula over here. And remember, we already discussed why we have no couple, so the second term is going to drop out. Basically, what we have to do here is just calculate the moment from each of these forces about point A. So the resultant moment about point A is going to be equal, right, to the sum of those moments. So let's going to start again from left to right over here. So I'm at A, the first force that I encounter is this 200. So 200 is the force. The distance is 3 feet. So remember, moment is force times distance. We got the force, we got the distance. Next is the sign. So if I'm at point A, and this is my force over here, 200, this guy's going to try to make the beam kind of rotate counterclockwise like this. So with the right hand, remember, if you have a thumbs out, or if you're working this on your sheet of paper, a thumbs up, that's a positive moment. Remember, counterclockwise is a positive moment. So as we continue now, we have this guy over here, 80 pounds. So 80, not times 3 now, but the distance to this one is going to be 3 plus 3 or 6. This is too messy. So 80 times 6. This 80 is pointing down, so if I'm at A over here, that's going to make it spin clockwise, right? Which is a negative moment. Next force is the 60 pounds. So that's the force is 60, but what is the distance, right? Well, if we extend the line of action, or we slide the vector that we were learning, right? That vector passes through point A. So essentially its moment arm is 0. So the 60-pound force does not contribute, or does not create a tendency to rotate above point A. This 25-pound force, which also passes through point A, same thing, it's not going to contribute. So all we have to worry about is this last one, which is 43.3 times the distance. So this is 3 plus 3 plus 3, which is 9. Next is the sign, right? Is this positive or negative? When we take a look with our right hand, it's going to make it spin counterclockwise, which makes it a positive moment. So remember, there's a point over there. So now all we have to do is type this in the calculator. So 200 times 3 minus 80 times 6 plus 43.3 times 9. And if I didn't make any fat finger mistakes, I get 509.7. Remember the units, these are pounds and feet. So pounds. Also, this moment is a positive number, which means that this guy is going to be a counterclockwise moment over here. So as we draw it, it means we have the counterclockwise moment like so, and this has 509.7 pounds. So we have the first part of the problem done. We figured out the equivalent resultant force and couple moment acting at A, right? We've done that simplification from all these forces to just a force and a couple moment. Next, we want to further simplify it. So we want to just one force that is going to create the same external effects. So basically what we do is we can take this resultant force and we can move it here to the left or to the right until we're right at the exact distance from A that it'll create the same tendency to rotate as this couple moment. So now let me ask you, we have this resultant this resultant force pointing this way. Should we move it here to the left of point A or to the right? Correct. If you want the rotation in this direction, right, I need to move this force this way, so it'll cause the same counterclockwise rotation. Right? So at the end of the day, oops, this is crooked. That's our moment, that's our B, that's our point A, and we need to move this guy, just 184 pounds force, some distance. And so the question is going to be, what is that distance? Well, the answer is simple. Remember, this force here is at an angle, right? So it's going to have X component and a Y component. And the X component of the resultant force passes through point A, so it does not contribute in making a rotation. So only the Y component is going to contribute. So if you remember the formula, right? Moment is just force times distance. Here we're solving for the distance, right? So this is just m by f. Specifically for this one, this is the moment at A, the resultant moment at A, divided by the resultant force. But not the whole thing again, we just want the y component. So that's the y component. Right, so our resultant moment over here was 509.7. And the y component of our force, if you remember, the y component was 163.3. Now check out the units, right? The moment has unit of foot-pounds. This has units of pounds in the bottom, so pounds cancel. And this is gonna give us a distance here in feet. So 509.7 divided by 163.3 gives a distance of 3.121 feet. So again, that is our distance here. This distance, 3.121 feet. So just to recap, we started with a problem over here. Our job was to find the equivalent resultant force and couple moment at A, and then to further simplify with just the force. So we go ahead and tackle these problems by doing a free body diagram, right? Getting any x or y components of the forces is going to help us very quickly calculate the resultant force, which is just the sum of the forces in the x and the y. And then the resultant couple moment at point A. Remember, we always have to watch out for any moment that does not pass through the point of interest. See what its contribution is going to be, plus any couple moments. In this example, we had any. As always, if you find any mistakes in my calculations or you have any general questions, you can drop a comment down below.